Okay, this is going to be the video for Calc 3, section 15.8 on spherical coordinates. This is the last section in chapter 15. And this is just another coordinate system that's convenient to use whenever you have spheres and certain kinds of conical shapes, just similar to the cylindrical coordinate system works whenever you have something that has a circular cross-section in one plane, but it's linear in the other direction, so something like a cylinder. So just to compare, we know that with rectangular coordinate systems, we just use the regular x, y, z, and we have 6 different ways that you can write the dv, but basically the basic one is just dx, dy, dz. In the last unit, we learned cylindrical coordinate system, and basically the idea there is you pick one of the planes, we'll just use x, y, and you do polar coordinates in that plane, and then in the other direction, you just keep z unchanged, right, so that that's linear. Right, so the idea is that to find any point in space, it's going to be on the surface of a cylinder, right, where we've defined an angle around the circumference of the cylinder, theta, counterclockwise from the positive x-axis toward y. And then to get the other dimension, you just go up from the xy plane, positive z. Right, so you're finding points that are always on the cylinder. The radius is labeled r, and that radius is in the xy plane, or perpendicular it's in the direction that's parallel to the xy plane. And we can convert because we know r squared is x squared plus y squared, so we can calculate r, and we know that theta is the tangent of y over x, z is always z, but mainly we use these conversion formulas, right? If you want to convert an existing equation in terms of x, y's, and z's to cylindrical, you have to replace the x's with r cosine theta, the y's with r sine theta, and then you leave z alone. And then the volume element is r dr d theta times dz, right? Okay, so now in spherical, we're going to say, what if it's the volume we're integrating over is not just circular in one plane, but it's circular all around. So we want to do something like polar all the way around for all of the variables. Well, then what we're going to do is define 2 angles, and we're going to locate a point on the surface of a sphere instead of on the surface of a cylinder. So if you imagine that you defined a point on a sphere here, okay, and to get to that point, you go a distance out directly from the origin to that. So that's a radius, but it's not a radius in the xy plane. It's a radius through 3D space. So that radius, we're going to change the letter for that to the Greek letter rho, which looks like that, kind of a weird looking, almost a P shape, but it's rho. Okay, so that's the radius directly from the origin to the point on the surface of the sphere. And we'll still have the angle theta, which represents the counterclockwise distance around on the xy plane. That's theta to get to the plane that contains this point. But then instead of defining up as a distance, we're going to define that as an angle down from the positive z-axis. So this angle here is called phi, okay, and it's written like that. Hopefully I won't do this, but I may mispronounce this phi, and that's just because the first time I learned it, the professor pronounced it wrong, so it went in my head the wrong way. But anyway, it's phi, like phi theta kappa or phi beta kappa or whatever, right? It's phi, and it's measured as an angle downward towards the xy plane from the positive x-axis, like this. Sorry, the positive z-axis. So this angle is phi. And then the angle theta is in the xy plane, and then the radius is now in 3 dimensions here, rho, not restricted. So just like r squared is x squared plus y squared in cylindrical, rho squared is x squared plus y squared plus z squared. And if you ever need the formulas for finding the angles, you could use them. But usually I just remember these formulas here for converting from spherical back to rectangular to replace, because often we're replacing x's, y's, and z's. And so we'll drive why these things are true in a second. But it turns out that the z coordinate here, this z coordinate here, is rho times the cosine of the phi angle. Okay, and then the x and the y are rho times the sine of the phi angle, and then times cosine of the theta angle or sine of the theta angle. So if you just remember that r is rho sine phi, then that means that, x is still r cosine theta, except that now r is rho sine phi. So x is rho sine phi times cosine theta, and this is r, this rho sine phi. So y is r times sine theta. Okay, and then we're going to show that the volume element turns out to be rho squared sine phi d rho d theta d phi. Okay, so let's actually look more closely at that geometry to see why those things are the way they are. First, let's imagine that we were to draw, we have a point defined somewhere here. It happens to be in the first octant, an angle theta counterclockwise towards y from the positive x-axis, and angle phi downward towards the xy plane from the positive z-axis, and then rho distance out to the point on the surface of the sphere. So if we define this purple plane here as a plane that goes through the point, but is perpendicular to the xy axis, and I'm drawing it over here, then that means that we can use this angle phi to define distances here. So this distance here is going to be rho cosine of phi. The reason for that is because if this angle is phi, then because of the geometry alternate interior angles are congruent theorem, this angle would also be phi. That makes this side the adjacent side for this right triangle, right? And that means that this would be the hypotenuse times the cosine of the angle. So rho cosine phi is z. That's this height here. Z is rho cosine phi. Okay. All right, and then the opposite side of that triangle would be rho sine phi, right? And that's the reason why rho sine phi is equivalent to r, right? R is rho sine phi. All right. All right. And then now that we know that rho sine phi is down here, let's figure out what the x and y coordinates are. So if you plot a look down on the xy plane down here, you would get this. This rho sine phi is here, and this is angle theta. So that means that since this is equivalent to r, then the x component is just r, which is rho sine phi, times cosine theta, and the y component is r, which is rho sine phi times sine theta. So that's how we derive these formulas here, that, that x is rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine phi. All right. And then the volume element is a little trickier to picture. So first of all, we know that there is a kind of a box that's semi-rectangular here, and one of the dimensions is just change in the radius. So we'll call that maybe the height. That's the d rho, right? We also know that if this angle here is phi, then if you have a change in phi, so like a d phi, then to get that angle to be an arc length, you have to multiply by the radius there. So that's going to be rho times d phi. So rho d phi is another little length here, right? And then the last angle is actually down here on the xy plane. So the d phi has to be connected with a radius of rho sine phi. So the final width is rho sine phi times the angle, the change in angle d theta. So rho sine phi d theta gives this distance here, like this distance here. All right, and so if you multiply it all together, you end up having two rows. So rho squared, a sine phi, and then d phi d theta d rho d phi d theta d phi, in whichever order. Okay, so there's actually a typo in the notes that were published. If you're going to do some sort of a volume, or where this integrand is 1, or if you're going to sum up something over this volume, so you have a function of x, y, z, then the volume element has to change to, this is missing a row. It's rho squared sine phi d rho d phi d theta, okay, or d theta d phi. But then you have to convert the x in your multivariable function to rho sine phi cosine theta. The y has to be converted to rho sine phi sine theta, and the z has to be converted to rho cosine phi, so that everything is in terms of the spherical coordinates. All right, so that's the kind of definition of all that. Let me close this real quick and reopen it because I'm having kind of some weird things drawing it. Here, we're going to look at some examples, mostly just kind of set up things, and then we'll do one integration problem at the end here. But let me open this up again. And I want to go ahead and do the problems. Okay, so let's look at some example problems here. And I'm going to represent this. Hopefully the problem with my pen will go away. All right, so you could be asked various questions. Mainly we use this to do integrations, but let's just explore a little bit about the coordinate system itself. So let's say it says plot the point whose spherical coordinates are r pi over 2. So first we have to know what the default order is. Rho is always listed first, and then typically theta is next, and then phi. So in order, we've encountered theta all the way back with two-dimensional coordinates. So that's the one that's first. The new angle here for spherical is phi, so that's the one that's last. So this is telling me rho is 5, theta is pi, and phi is pi over 2. So if I was going to graph this, we do our graph in rectangular. I know I'm going to end up going a distance phi, but or 5. But first, let's use this pi right here. So we're going to go to the angle pi, and theta is defined in the xy plane. So we're going to go. Let me extend this back here. We're going to go around an angle theta in the xy plane, and then we're going to go down pi over 2, right? So pi over 2 is down from the z-axis. So from the z-axis, we'll go down pi over 2 from there. And then we need to go a distance 5 out in that direction. So 1, 2, 3, 4, 5. So this happens to be a point that's on the negative x-axis down here, like that. And if we wanted to find the rectangular coordinates of that, we could use the formulas. So x is r, which is rho sine phi, but then times the cosine of theta. So that's going to be 5 times the sine of pi over 2 times the cosine of the theta angle pi, right? So let's see, a little unit circle here. I wish my, let me try one more thing here. Well, I'll do this after this problem is done. Sine of pi over 2, so pi over 2 is up here, sine would be 1. And cosine of pi is over here, cosine would be -1. So this would in fact be -5. That's the x-coordinate. The y-coordinate would be r cosine, or r sine theta, but r is rho sine phi, sine theta now. So the 5 times the sine of pi over 2, that part's not going to change. But now we have sine of pi. So that's going to be 5 times 1 times 0, or 0. So the y-coordinate is 0. And then for z, it would be r cosine phi, right, which is 5 times the cosine of pi over 2. And at pi over 2, the cosine is 0. So this is 0. So this is the point in x -5, in y 0, and in z 0. Okay? All right. Okay, I'm going to correct something with my board real quick, and we'll be right back online here. Just 1 second. Okay, and if this doesn't fix it, I'll stop messing with it. It just the pen keeps interrupting when I'm writing, so it's easier if I can have a smooth writing tool. All right, so that's the first example, and all we're doing there is just plotting points. All right, let's take a look at some other examples. Okay, what if we wanted to change this from rectangular to spherical coordinates? So, of course, in rectangular, this is definitely giving me x, then y, then z. And we want to go the other way around. So first of all, let's go ahead and find rho. We know that rho squared is x squared plus y squared plus z squared. Okay, so rho squared would be, well, rho, let me just do it that way. Rho is the square root of the x squared plus the y squared plus the z squared. And so that would be the square root of 1 plus 1 plus 6. So let's see if we got the square root of 8. Or if you're looking in the book, they would probably call that 2 square root of 2. Okay, so we know rho, and then we have to figure out the other angles. So we could get the phi angle from the fact that z is cosine, sorry, is rho. Z is rho cosine of phi. So if I know that z is square root of 6, and I know rho is the square root of 8, then I could calculate what the cosine of phi is. Cosine of phi is the square root of 6 over the square root of 8. Could I turn that into some like standard form, where we know that this is square root of, let's see, square root of 6 we have over the square root of 8. That's the same as the square root of 6 over 8, right? Which would be the square root of, let's see, you could factor 2 out, right? So 3 over 4, the square root of 3 over 4. Is that right? Yeah, and you know what we could do? You know what? Let's do this. Let me back up a step. Let's do this. Let's write this as the square root of 6, square root of 6, and then the 2 square root of 2 form, because then I could have 1/2 the square root of 6. Is that right? I'm just thinking we should be able to, did I make a mistake here? Let's see, square root of 6 for z, rho is the square root of 8. Yeah, we should be able to determine that this is the square root of 3 over 2, I think. Yeah, why am I not seeing that? Okay. Square root of 6, square root of 8, cosine phi, square root of 6 over 8. Oh, I see. Okay, so square root of 3 over 4. And then I'm going to split this on the bottom to, this is going to be 2 times 2. No, because if I pull it outside, it's, yeah, that's right. Okay, duh. Sorry. This is the square root of 3 over the square root of 4, which is square root of 3 over 2. There we go. Okay, so since I know cosine phi is the square root of 3 over 2, where on the unit circle would the square root of 3 over 2 appear for the cosine? Right, so the cosine is x, so that would be up here. And the inverse cosine always produces angles up here. So in fact, it would be the one that has the large x, which is over here, right, at pi over 6. So from using our knowledge of the unit circle, we can figure out that rho has to be pi over 6, so that the cosine of, sorry, that phi is pi over 6, because the cosine of phi would be square root of 3 over 2. All right, and then once I know what rho or what phi is, then I could use one of the other angles, like let's use y. We know that y is r cosine theta, but we know that r is rho sine phi cosine theta, right? So if we know that y is 1 and rho is the square root of 8, and we've got that phi is pi over 6, we should be able to plug all that in and then compute what theta is. So what is sine of pi over 6? That's 1/2. I wish my pen would work. So so this is actually the same as the 2 square root of 2 over 2 cosine theta. These would cancel, and so you'd have 1 over the square root of 2 equals cosine theta, which if you multiply top and bottom by square root of 2, you're going to get the square root of 2 over 2 is the cosine of theta. And on a unit circle, where is the x, the square root of 2 over 2? Well, that would be at pi over 4. Right, so it looks like theta is pi over 4, phi is pi over 6, and rho is 2 square root of 2. So this is equivalent to rho is 2 square root of 2, or square root of 8. That's the rho. The theta would be pi over 4. Usually that's written next. And then finally the phi angle pi over 6. is that. All right. All right. Let's go ahead and work a couple more problems here. Okay, this turns out to be important because often we have equations for the multivariable function or sometimes surfaces for boundaries, but they're usually expressed in terms of rectangular coordinates, and to be able to use this in an integral, we have to convert everything to spherical. So how would we convert this equation, z squared equals x squared plus y squared, into spherical coordinates? Well, the first thing I might recognize is that this right here is r squared. And I know that r in spherical is the same as rho sine phi, right? And then z, we know that is rho cosine phi. So this is a spherical version of this equation. And that's one way. At this point, we've met the criteria. We've written this in spherical coordinates, but there's other forms that might be more helpful. Like maybe I could say, okay, rho squared times cosine squared phi, therefore, is equal to rho squared times sine squared of phi, right? So that means either rho has to be 0, or actually, let me show one more step here. If I were to get everything on one side, rho squared cosine squared phi minus rho squared sine squared phi, I don't want to remove any information, so I won't cancel things out. But if you were to factor out a rho squared, then there's actually two possibilities. Either rho is equal to 0, or cosine squared phi has to equal sine squared phi. Those are the two possibilities. So this equation would be true if rho was 0. If you were at the origin, it would be true that the z coordinate would be equal to x squared plus y because everything is 0. That's kind of the trivial solution. So it's more that cosine squared of phi has to be equal to sine squared phi, right? And if you were to do a little manipulation here, you could therefore say sine squared of phi over cosine squared of phi would have to equal 1, right? Which is the same as saying that the tangent squared of phi has to equal 1, which is the same as saying that tangent of phi has to equal plus or minus the square root of 1, which would be plus or minus 1. So there's two possibilities here. You could have tangent of phi equals 1, or you could have tangent of phi equals negative 1. And what would that look like? Well, where are angles tangents equal to positive 1 on a unit circle, wherever the x and y are both positive or both negative? So at pi over 4, and at 1, 2, 3, 4, 5 pi over 4. And then the tangent of phi would be negative 1 at 1, 2, 3 pi over 4, 4, 5, 6, 7 pi over 4. So another way of writing this equation besides kind of this way would be to say it's equivalent to saying tangent of phi equals pi over 4, or 3 pi over 4, or 5 pi over 4, or 7 pi over 4. Okay, so depending on what we're using, all of these are various representations of this equation. These things have to be true for this equation to be true. So in a sense, they are the spherical version. Although even this is a correct answer to the question because we've changed all the x, y's, and z's into rhos, phi's, and thetas. All right. Okay, sketch a solid that's described by rho is less than or equal to 1 and phi remains between 3 pi over 4 and pi. All right, so let's grab a rectangular coordinate system here, x, y, z. We'll do the rho last. They're not specifying theta, so that means we can go all the way around in the theta direction, but we're supposed to start and stop at certain places for phi. So we start at 3 pi over 4 and we end at pi. But remember, phi is defined downward from, or towards the xy plane from positive z. So we'd have to go starting all the way down here at pi over 3 pi over 4, and ending when we got to pi. So it's this region here, right? Except spun all the way around. And we're only going to go out to rho as 1 or less. So this distance is 1. So essentially what it is it is a cone, a conical shape down here, but all the way out to the row of 1. So it's really like a snow cone shape, right, with a rounded edge here. And it's all of this space inside that snow cone shape, including out to the rounded edge. Okay, that would be the solid that's described by this, kind of a lower portion of a snow cone, or a snow cone, opening downward with a curved top that has a radius of 1 everywhere here, right? It goes all the way around, but it starts at 45 degrees below the XY plane, where phi is 3 pi over 4. Okay. All right, and then I have one last example. This is more the way we use this is for doing volumes and things like that. Problem 15 from the book, which is similar to some of the homework problems, says a solid lies above the cone z equals square root of x squared plus y squared, which is z squared equals x squared plus y squared, but only the positive z portion of that, okay? And below the sphere x squared plus y squared plus z squared equals z. Write a description of the solid in terms of inequalities involving spherical coordinates. So find out what the boundaries are using rhos, sines, and phis. And then I added on, let's find the volume of this solid. Okay, so first maybe we could sketch what's going on here. Okay, we have our XYZ coordinate system. And we have a sphere, but you know what? First, that sphere is not located at the origin because this is not a number out here. This could be brought over to this side and complete the square. So let's actually do that first. If we have x squared plus y squared plus z squared equals z, and we brought the z over to the left side, and I wanted to complete the square here. Actually, let me leave a little bit of space here. So equals 0. I'm going to take this and convert it into a perfect square. So I have x squared plus y squared still, but I want to write this as z plus or minus something squared. Okay, so the completing the square procedure would be we would take this -1 here and cut it in half to make it -1/2, square that number up here, which would be 1/4, and since we put a 1/4 times 1 on this side, we have to balance it with a 1/4 over there. Right, so this would be this, and that means we have a sphere whose center is not at the origin. The center is at 0 for x, 0 for y, but 1/2 for z, and the radius of this sphere would be the square root of 1/4, which is 1/2. Okay, so now that I got that, let me go ahead and draw this. So it's centered a half up, and then the radius is a half up. So if this was a half here, and this was 1 up here, right, that sphere would look like this. Right, it's a sphere centered at the point 0, 0, 1/2 with a radius of a half. So it's just touching the origin down here like that. Okay, and then there's a cone, z equals the square root of x squared plus y squared. So this cone only has positive components. So even though cones usually go up and down, we're talking about the positive component by itself. Let's see. So it's going to expand here. We might want to know before we sketch it in, where is it going to intersect this sphere? So maybe we could take a look at that. Where would this and this intersect? So if I know that z squared, oh, I don't know, do we have to do that? It's going to be a lot of work. So I'm going to go off here, possibly in the weeds, to to look at something just before I sketch this, because I have a feeling that this touches right here at the maximum radius, but I'd like to kind of prove that to myself. The maximum radius in the parallel to the xy plane of the sphere. So if I know that x squared plus y squared plus z squared has to equal z to be on the sphere, and I know that z has to be the square root of x squared plus y squared, I should be able to plug this z into this equation and find the intersection. Let's just do that real quick. So that would give me x squared plus y squared plus z squared, and then that's this squared, which would then therefore be x squared plus y squared, equals z, which is the square root of x squared plus y squared. So that gives me 2x squared plus 2y squared equals the square root of x squared plus y squared. All right. Let's see. I could factor a 2 out here, and I would get x squared plus y squared, square root of x squared plus y squared, right? If I were to square both sides, would that help at all? Then I would have 4. No, that's not really going to help. I'm just trying to convince myself here that that where this goes without having to plot it, but I'm not seeing a real quick and simple. Well, I guess okay. So assuming that, well, so this intersection is not going to occur where x or y is 0. So I think if that's true, it would be legitimate for us to divide both sides by x squared plus y squared. Then I would have, let me move the 1/4 out here, or the 4 out here. I would have 1/4 here. Then I would have x squared plus y squared squared over x squared plus y squared. And so that is equivalent to, just continuing this, x squared plus y squared equals 1/4, which would be a radius of 1/2. So sure enough, that intersection does occur out here at 1/2. So if I draw the cone in there, I'll use green. The cone is going to intersect right at that location there. So we have a cone, right? Only the positive z portion of the cone. All right, so we have a solid that lies above this green cone, but below the sphere. So let me use red to highlight the area. It's this portion here. It's got the snow cone top and the cone edges here. This is the area. The area inside that red cone is the solid that's being described. Okay, so now that we know what it is by sketching it, let's figure out how to bound that with spherical quantities. Well, if I'm trying to cover that in spherical, I could imagine drawing like we would an integration line. Let me draw it here from the origin, integrating out until we get to the edge of the sphere, right? And that means rho is going to go from 0 out to the sphere, but we have to express the sphere equation as an equation in spherical coordinates so I can solve it for rho. So let's take the spherical equation as originally defined, x squared plus y squared plus z squared equals z. And I'm going to substitute expressions for rho and sine and phi here. So this left side is just equal to rho squared. And z is rho cosine of phi. So as long as rho is not 0, which will only be at this point here, but for everything, we're really trying to find the edge here, this edge. So rho is not 0. It's legal for me to divide both sides by rho and get that rho equals cosine of phi. So this is the equation of this surface here, rho equals cosine of phi. So I could state that rho has to stay between 0 and cosine of phi, okay? And then to complete this, I would want to say, okay, well, what do theta and phi need to be? Well, for phi, we're going to start at phi equals 0, and then we want to go down here until we get to this location right here. So I'm going to have to figure out where that stops. All right, so we have, Well, let's look at the geometry here to do that. So I'm going to look actually on the ZY plane. Let's take a look at the ZY plane here. Right, we've got at this spot right here, we've got a line here, right? We said that the radius down here was 1/4. So we've got a distance 1/4, right? And we are at 1/2 high. Is that right? I don't think that's right. Now we're at a half high. I'm sorry. Yeah, the radius is 1/2. Yeah, the equation there of that intersection was x squared plus y squared equals 1/2, which means the radius is the square root of 1/4, sorry. 1/4 square root of 1/4 is 1/2. So that means this is 1/4. Okay. I'm sorry, 1/2. I keep misspeaking. So if I were to draw a little triangle in there, okay, and say I'm after this angle, right? An angle where we have the two lengths are equal, that is a 45-degree angle there, right? Which in radians is equivalent to pi/4. So that means that my phi has to go from, let me go back up to the sketch. We have to go from phi equals 0 down here to phi equals pi/4. 0 to pi/4. Okay, and then theta is the easy one because in theta, we're just going to go all the way around the entire object. So for theta, we're going to have that constricted from 0 to 2 pi. Okay, so the problem as originally stated, we had to go through all this kind of geometry stuff and substitutions to get everything in terms of, and probably the trickiest one was this, to get what the surface edge looked like for the sphere in spherical coordinates for rho, solve for rho. But now that we have these boundaries, we could just find the volume. Now to find the volume, we're just going to do a spherical integral with the integrand set to 1 of this. So let me go further down here, and we'll write an integral for the volume. So the volume would be a triple integral where theta is going to go from 0 to 2 pi. Actually, typically we do a phi on the outside. So let me just do it that way to kind of follow convention, although it doesn't really matter if there's no dependencies. Theta is going to go from 0 to 2 pi, and then the rho is going to go from 0 to cosine of phi. The only real direction here is that since phi appears here, you have to do the integral containing phi before you get to the integral for phi. Since we're doing volume, we're just going to do an integral of 1. This would be d rho, d theta, and then finally d phi on the outside. Okay, so we would do these iteratively from the inside out, starting with the d rho one. We're just going to have integral from 0 to cosine of phi of 1 d rho, right, which is just going to be rho from 0 to cosine of phi, which is just going to be cosine of phi minus 0, so it's cosine of phi. Okay, the next integral out would be the theta one. And so we're going to go integral from 0 to 2 pi of cosine phi d theta. But while we're doing theta, cosine phi is just a constant, so it comes outside of the integral. It's just 1 d theta, so it's cosine theta as a constant. Sorry, cosine phi theta from 0 to 2 pi. So we're just going to end up getting 2 pi minus 0, which is 2 pi. So the result of this is 2 pi times cosine of phi. And then the last integral, the phi integral, would be the integral from 0 to pi over 4, we said, I believe, right? Yep. And we're going to be integrating 2 pi, so the 2 pi comes out. That's a constant, but it's cosine of phi d phi. Okay, so the antiderivative of cosine is sine. So we have sine phi here from 0 to pi over 4. I actually have to plug these in, so I have 2 pi. I'm going to have my two copies, cosine or sine of something minus sine of something. But we would plug in pi over 4 here and 0 here. And so on a unit circle, pi over 4 is here. The sine of that is the square root of 2 over 2. And down here at 0, this is 0. wait a second, just 2 pi out here. So these 2's will cancel, and we're going to get, let's see. I got something. Oh, I messed up here. Does anybody see my mistake? I made a really, really bad error here. So we're going to have to redo that integral. And the problem was that I didn't put the correct element out here, right? It is true that we have d rho, d theta, d phi. However, right, whenever we're doing spherical, it's not just d rho, d theta, d phi. It's rho squared sine phi d rho, d theta, d phi. So good thing that I made the mistake now. That means now that you've seen it, you will not make that mistake when we get to the test, right? Okay, so let's do this properly now. We're going to do the integral on the inside first. So the inner integral would be from 0 to cosine phi of 1, or just rho squared sine phi d rho. Okay, so the sine will come out. That is a constant while we're working on integrating rho. So we've got 0 to cosine of phi rho squared. So a little bit more complicated. So we have sine phi. And then we have 1/3 rho cubed. I was going to say, I thought this was more complicated than what that was working out. So we're going to have our sine phi times 1/3 something cubed minus 1/3 something cubed with cosine phi filled in here and 0 here. So this is 0, but we're going to end up with 1/3 sine phi cosine cubed of phi. Yeah, that'll still be doable, but more involved. Okay, let's do the next level integral, which is 0 to 2 pi for d theta. So the d theta is going to be the integral from 0 to 2 pi of this. But while we're working on theta, everything here is just a constant, right? So let me move this over a little bit, because all of that is a constant. We just have 1/3 sine phi cosine cubed phi. But then we're doing integral from 0 to 2 pi of 1 times d theta. Okay, so we just get this part here just becomes 2 pi minus 0, so we end up with 2 pi over 3 times sine phi cosine cubed of phi. That's the result of the middle integral. And then for the phi integral, it's 0 to pi over 4. So for the phi integral, it's going to be, well, the 2 pi over 3 is definitely a constant, but we have to go from 0 to pi over 4 of, let me write it this way, cosine cubed phi sine phi d phi. And so here I think this is set up for a u substitution. So we could do a substitution. U is cosine phi because it's inside something cubed. Du would be the derivative of cosine is negative sine phi d phi. So therefore sine phi d phi is equal to negative du. And so if we substitute here, we're going to have u cubed negative du, right? And then for the integration limits, when we put 0 in here, u will be cosine of 0, which is 1, right? Or if we put pi over 4 in there, cosine of pi over 4 is the square root of 2 over 2, right? So square root of 2 over 2. And if I wanted to eliminate the negative, I could reverse the limits of integration here. So I'd have 2 pi over 3 integral from square root of 2 over 2 to 1 of just positive u cubed du. So we've got 2 pi over 3, and I've got 1/4 u to the 4th, right, from square root of 2 over 2 to 1. So actually, let's see, this 2 and this 2 cancel, so we would end up with, let's see, we'll end up with pi over, and then that'll be 6, right? 2 over 4 is 1/2 times a third is 6th. And then we would have 1 to the 4th minus square root of 2 over 2 to the 4th. Right, so this is going to be 1 minus 4 square roots of 2 multiplied, right, is going to be 2 times 2 is 4. And then 2 to the 4th is 2 times 2 is 4. 4 times 4 is 16. So this is going to be 1 minus a fourth, or 3/4, times pi over 6. So the final answer is pi over 8. The volume is pi over 8. All right. So that's how we do use the spherical coordinates to do an integration. And be careful to not do what I started doing. Remember that the volume element is not just d rho d theta d phi, it's rho squared sine phi times that. This is dv. Okay. If we had something other than volume, if we had a function here, we would have to convert the x, y, z's in the function into rho sine, or rho thetas and phis as well. So these problems can be really a challenge to integrate. Remember, you have the integration table available too if you encounter something that's just way too hard. All right, that'll be it for this video. We'll go ahead and give the problems a try, and we'll spend some time in class working problems as part of our review.